Last lesson of the semester, last lesson of this side of calculus, this differential calculus called related rates. And this is where we introduce time in, and we see how all different variables impact each other. If you change one variable in this timing, then how will that impact something else? So everything is related, everything is connected. You can't change one thing without impacting something else. All right, so that is our idea today, introducing the time differential. Taking parametrics but putting it into motion, okay, actually activating it, learn how everything is interconnected. All right, so you were introduced to the idea of a differential yesterday, a dx. A dx stood for what?
The displacement of x, like the distance.
Okay, how much x changes, okay, and that impacts the dy, which is how much the y changes. And now we're going to be bringing into it the dt, okay? And the dt is the change in time. We're just not going to be changing, sometimes we'll be changing time a lot, sometimes we'll just be changing time by a millisecond. Okay, so, but we are changing time, and any change in time is going to have an impact on the situation. So as soon as we do this, we're putting time in motion. I like to think of it like, you know, the live pictures that you take, and then you can, so sometimes you're just seeing the freeze frame, but then when you hold on it, you can kind of see what's all going on sort of before or after, or doing a burst and having a burst of a situation, coming up with 37 pictures that are all happening within that, but then picking the one. Okay, so when we stop time, we freeze it. When we activate time, then the situation is going to be in motion. All right, so let's talk about something that is not moving, which would be a sphere, and then let's put it in motion using calculus. All right, so we're going to start with the surface area of a sphere. This is not something I would expect you to know. It would be something I would give you. But interestingly enough, if you had to figure it out, the surface area of a sphere is connected to the volume of a sphere. So does anybody know the volume of a sphere? 4/3 pi r cubed. The surface area of a sphere is the derivative of that. Okay, so, but I would give you that. So the surface area of a sphere is S, we'll call that for surface area, is the derivative, so 4 pi r squared. All right, now, if we want to figure out how the surface area of the sphere is changing, so maybe your sphere is a soap bubble, and the soap bubble is losing air, and so it's getting smaller. Or maybe you're blowing into the soap bubble and it's expanding. So the surface area is changing, so we're putting the problem in motion. And to put the problem in motion is you introduce time, and you take the derivative of the problem. So what are the variables right now? Radius, okay, and s. Okay, those are our two variables. We're going to bring in the third variable, and the third variable is time. And the way we do that is we take ds, and our derivative is with respect to time, not with respect to dr, but with respect to time. Remember that there's implied parentheses in this problem around your r. Okay, so keep that in mind, implied parentheses. Okay, 4 is what kind of a number? Constant. Pi is what kind of a number? A constant. So they just sit there. What do I do with the square?
You bring it to the front.
I do. I pull it to the front because I'm taking the derivative. So what will I end up with? Okay, 8 pi. And then in the parentheses is still r, and what's the power on that now? To the first. But because it's still in parentheses, what do I need to remember? The chain rule. And the chain rule would be what's the derivative of what's inside the parentheses. And so the derivative would be dr relative to dt. So it's this differential of t. That is now a problem in motion. That's how time would impact those two variables. That's all we're going to do right now, just practice taking the derivative. So everything is over a dt every time you take a derivative. Let's try another one. All right, suppose you have a block of ice that's a perfect rectangle right now, but it's starting to melt. Okay, it's a block of ice that's rectangular, but it's starting to melt. What is that going to affect as it melts? It's going to affect the volume, but what else is it going to affect? The surface area. What else? If it melts, what's happening to the sides? Are the sides staying the same? What is happening to them? They're shrinking, they're getting smaller. So all the things are changing. The sides are changing, the volume is changing, the surface area is changing. All right, so we want to think about this rectangular block of ice. So we've got the volume of a rectangular block of ice. And I didn't tell you that it has a square base or anything. It's just simply a rectangular block of ice. So all three sides are different. So you have the width, the length, and the height. And then for surface area, okay, thinking of this as a rectangular block of ice, anybody want to take a stab at that, the geometry on that? How many sides does this have? 6, okay? And so how many of them are the same?
4 of them are.
Only if you have a square bottom. Okay, I have pairs. Pairs are the same, like the front and the back are the same. Okay, so we've got, they're not all the same. So what do we have? How would we describe the surface area of a pair of sides? 2WL or LW, and then what else? Plus 2WH would be another set, and then, okay. This is the geometry on that, okay? This is not in motion. Nothing's happening to this. It will get in motion as soon as I take the derivative. And so I am going to do dv dt. So time is going to impact that. Now, how am I going to take the derivative of W times L times H? Product rule, but what kind of fancy product rule? The triple product rule. Okay.
There's a triple product rule?
Well, we've talked about that before. Yeah, we've talked about that before. Okay, so when you take the triple product rule, okay, it doesn't really matter what order you do it in, but you keep 2 of them the same and then take the derivative of one of them. Okay, so W and L and dH dt. And then you add to that, because this is a product, a different combination. So give me another combination.
WH.
W and H, and then what would be impacted by time that time? DL dt. And then the third one would be the final combination we haven't covered yet.
D or
So
HL.
L and H, or H and L, and then dW dt. Okay, that is this motion affecting the volume. Now I want to talk about units here. Every differential has units. So looking at your dV dt here at the beginning, what are the units for volume? Okay, cubic units, right? Did I tell you? Okay, so we'll have units cubed. Okay, and then we need units for the denominator and the units for time. Okay, so all your units are going to be expressed like cubic centimeters per minute or cubic feet per hour, or it'll be some kind of expression in terms of units and then time. All the other ones have different units because the height is not measured in cubic units. What's the height measured in? Regular units. And then time. But all of them have that that feature in common. And the units that you put are going to be important. You'll get docked if you don't have the right units for the differential that you're talking about. All right, let's look at surface area and how we would take the derivative of that. So we would have d of SA over dt. Let's think about those units a minute before we move on to the other. What units do you use to measure surface area? Square units. So that would be units squared, and then you'd have your time units here. So every time you have a differential, you got to think about what the units would be. Then we take the derivatives here of our of all the different products, but these are regular products. What do you notice all of these have in common? A 2. So I could maybe factor the 2 out. And then I could tackle all of their individual derivatives. So the WL is a product. So that would be L dW dt plus the other combination of W dL dt. That's the first product. And then plus 2 times, and then the next product rule. So in any order, H dW dt plus W dH dt. the product rule of the multiplication. And then the last one would be h dl dt plus L dH dt. These are all called, all of these rates are related to each other. So if you only changed one side, how would it impact the overall surface area? How are they all related? Nothing is on its own. It all is connected to each other. Okay, these are the mechanics of that. Any questions on that so far? Okay. All right, so here's an actual one with numbers. So let's say we are working with a spherical soap bubble and we're going to blow air into it, and the rate of the air is going to be 10 cubic centimeters per second. How fast is the radius changing as you're pumping air into this? And then remember your units. Okay, so your order is geometry first, calculus second to put the thing in motion, and then only deal with numbers when you've done your other two things. One of the biggest mistakes people make is they try and plug the number 10 in too soon. Hold off on that, okay? Resist holding off, because 10 is a rate and it has to happen after the calculus has happened. All right, so our soap bubble here, and our soap bubble, look at the units you're given. If you're given cubic centimeters, what does that mean you're measuring about the soap bubble? Volume. So that is where you start. You start with your geometry of your soap bubble. So the volume in geometry is 4/3 pi r cubed. That's just a nice little soap bubble that's sitting there. Now we want to expand the soap bubble. We want to start the clock on the timer. Okay, time, start, time, go. I'm pumping in air. So then we're going to bring in our dv dt. So calculus second. Geometry first, calculus second. All right, I always, when I take my derivative, I always think about what the units are going to be here. So this is going to be the cubic centimeters there, and it's going to be the seconds on the bottom. So that's my cubic centimeters per second. So on my other side, I know 4/3 is a constant, pi is a constant, and so I'm ready to take the derivative, and remembering that I have implied parentheses around the r. So my derivative turns out to be, moving 3 to the front, 4 pi, and then parentheses r squared, and then the derivative of what's inside the parentheses, which would be dr dt. And then I remind myself of what the units are for that. And the units are going to be, for r, regular centimeters, not centimeters cubed, but regular centimeters, and time is still measured in seconds. Once I've done my geometry and my calculus, then you can start putting in your numbers. So where does the 10 go? The 10 is measured in cubic centimeters per second. So 10 goes on that side right there. That is your cubic centimeters per second. And then we have 4 pi r squared times dr dt. And the question is asking me, how fast will the radius change? So that it's asking me for a speed of the radius. So I just need to get this by itself in order to answer the question. And so I use algebra to figure out that it'll be 10 divided by 4 pi r squared, which reduces to be 5 divided by 2 pi r squared, and that is equal to dr dt by itself, which is measured in centimeters per second. And so the answer to the question is 5 over 2 pi r squared centimeters per second. Any questions on that one? Okay. Am I going too fast? Okay, let's try another one. Okay, consider a cylindrical tank that has a leak in it. Okay, so our geometry is a big tank. Have you ever, anybody drive down Palo Verde ever? And there's a huge storage tank of water where City of Lakewood keeps their, okay, so imagine that, this huge cylindrical tank, and somehow it sprung a leak. One of the rivets came loose or something. All right, how fast is the water level dropping in that tank as this is happening? All right, so let's think geometry first. So my geometry, I have this cylindrical tank here. We're looking at units to help us out, to help us know what geometry we're talking about. The units are liters, which is also converted to milliliters. And so if I'm measuring liquid in liters or milliliters, then I'm using volume, again, in this situation as my, my geometry. So I'll set up my geometry. Okay, I need to know what the volume of a cylindrical tank is. Okay, so the volume is always the shape of the base, and this shape is a circle. And so that would be pi r squared. And then times the value of the height, which we know to be h. So that's my geometry. And then we're ready to move into calculus. And as soon as you move into calculus, then this problem springs into action and something about it is moving. And in this case, it's the water that's moving. The water is leaking out. So we'll launch into calculus now, and we'll do dv dt. And my dv dt is being measured, and I have some units. I have either, I can use liters, or I can use milliliters, and that'll be measuring the volume. And then I have seconds that I can be using to measure the time. More often than not, you'll be using milliliters, because a milliliter is easier to translate over to like centimeters for length and height, like for radius and height, because a milliliter is equivalent to 1 cubic centimeter. So using that metric is always a little bit easier to use milliliters instead of liters. All right, and so let's do the calculus on the other side. Pi is a constant, so I don't really need to worry about that, but I do have a product here. And so as I take my derivative of the product, I'm going to start with h. And then I'm going to take the derivative of r squared, not just 2r. That's where it's tricky because there are implied parentheses here. So it's not just 2r. It has to be 2r something else. 2r dr dt. That is the place people, forgot the chain rule. Okay, that's where it comes into play. Okay, then plus, and then we have r squared times, and now we need the derivative of the other piece, which is the derivative of h, which is, it's not 1, it's dh dt. The only way it would have been 1 is if the derivative was dh over dh. That's the only way it's 1. And none of ours are over themselves. They are all with respect to time. And so we never have it be 1. The derivative's never 1 when you're using time. Okay, now we've done our calculus. Now we're ready to plug some numbers in and to answer the question. So we only have one number. The number we were given is 0.03 or 30 milliliters per second. I'm going to suggest that you use the milliliters, so we'll use 30. But I also want you to think about the situation here. The water is going in what direction? Down. It's leaking, right? It's leaking at a rate of, so you're not going to put in just 30. You have to put in negative 30 because this is a decreasing situation. The rate is going down. The water level is dropping. And so you have to be sensitive to signs when you're reading the context of the question. That would be a negative 30. Okay, and then we have, let's see, I'll distribute my pi, so I'll clean this up a minute. I have 2 pi rh that has a dr dt on it. And then I have a pi r squared that has a dh dt on it. Okay, now we have 2 rates left in the problem. We have a dr dt and we have a dh dt. So let's start with the dr dt. Dr dt is describing what about this problem? The change in the radius, okay? The r dt is describing the change in the radius. What is the dh dt? Okay, so now can you picture what's going on here? As the height changes, as the water leaks out, what's the water height doing? Okay, water height is going down. As the water leaks out, what's happening to the radius? Wait, nothing. The radius isn't changing because no matter, you just go down the cylinder, it's not like this is a cone. It's not like this is coming down. The radius is not changing. And so you also have to think about that. Not only do you think about the negative for the 30, but you have to think, this thing is not changing. Didn't spell right. If it's not changing at all, in other words, the radius is constant the whole time. The radius on the top is the same as the radius on the bottom. The radius is constant. Then the value of dr dt is 0. And because the value of dr dt is 0, that wipes out this entire section of the problem. And it simplifies it greatly for you because it's not changing at all. The radius at the top is the exact same as the radius at the bottom and the radius at the middle. There's no difference. Okay, whereas the height is changing as the water is being removed from this tank. So this simplifies our problem quite a bit for us. And we're down to just negative 30 being equal to pi r squared times dh dt. And so then my question, how fast is the water level dropping? That's where we're going to find this. dh dt represents the water level or the water height. And that question, that is going to answer our question. So that's what we want to manipulate to have a loan. And so we would say, okay, dh dt, if I get it alone, turns out to be negative 30 in the numerator, pi r squared in the denominator, and I've got to have units measuring that. Now, does this make sense to you that this would be negative?
Yeah.
Why?
Because it's leaking.
Right.
Going up.
And so the height is not going up, the height is going down. All right, what will the units be? So we need a unit for the numerator.
Milliliters.
Okay, milliliters doesn't measure a height. Centimeters measures a height. That's why we used milliliters. Milliliters measures a volume. Centimeters measures a height. And so our units on this would be centimeters for the numerator, and our time is still going to be seconds for our denominator. So our units are centimeters per second. So that all goes back to your science classes where you learn that 1 milliliter is the same as 1 cubic centimeter. Those two things are equal. And so if you're using milliliter for volume, then the corresponding unit for distance or length would be a centimeter. Yeah, Rose.
Actually, you just answered.
Okay, great. Okay. All right, here we go. A police officer and a suspect are engaged in a high-speed chase. Yes?
I'm sorry.
Sorry,
On
yeah.
the last one, how come it's not centimeters cubed over second?
Oh, very good question. All right, because when we're looking at the numerator here, the numerator is dh, and what did h stand for? Height. And height isn't measured in cubic centimeters. Height is measured in just plain centimeters. The only thing that's measured in cubic centimeters would be the volume of the water, but not the height of the water. Okay.
So then is a milliliter the same as 1 centimeter?
No, a milliliter is the same as 1 cubic centimeter. Milliliter is only a unit of volume.
So then why didn't we do any conversions when we plugged in the 30?
Because we used 30 measured in milliliters. If we had used,
Right, but that's equal to centimeters cubed.
right, so if you draw it, 1 cubic centimeter, like a sugar cube, okay? So that is 1 cubic centimeter. Its volume is called 1 milliliter, what it would hold on the inside. Those are equal.
So why didn't we answer?
Pi r squared is the other centimeter squared.
Oh, okay. Thank you.
Okay. All right, let's do the police chasing the suspect. All right, the police officer is chasing it. They're going down the same road, and then all of a sudden, the suspect turns a corner. Okay, so we have to imagine what's happening here. We've got the two chasing each other down this road, and then whoop, the police turns this way. So you've got the suspect is here, and you have the police down here. So we'll call that S for suspect, and we'll call that P for police. Okay, and they've turned the corner. The suspect is going that direction, and the policeman is going this direction. Okay, let's think about this a minute. If my little red dots represent the length of S for the suspect, what's happening to that length as the suspect is trying to get away? It's getting bigger, right? Because it's moving that way, so S is getting bigger. So we would expect ds dt to be positive. So I need you to keep that in mind. We expect ds dt to be positive, to be greater than 0. All right, the policeman, the blue. Okay, my policeman is going this way. As the policeman is pursuing the suspect, what's happening to the blue dots, the length of the side on the policeman's edge? What's happening to that? It's decreasing. Okay, the policeman's side should be getting smaller because the policeman's trying to get closer. And so we expect dp dt to be less than 0 because it's getting smaller. That side is getting smaller. Now we're asked the question, okay, the officer's going 80 miles an hour. We don't know how fast the suspect is going. The distance between them, okay, and where is the distance between them literally? The diagonal, right? This is the distance between them, so I'll do that as a black. What shape has just come out of this drawing? What kind of triangle specifically? A right triangle, and we'll call the distance between them x because we don't know what the distance is. And that is increasing at a rate. All of that to say, how fast is the suspect going? Okay, let's diagnose the problem. Geometry first. Well, what's the shape? Always go back to what the shape is. It's a triangle. What kind of triangle? Right triangle. What's the only things that work in a right triangle? Pythagorean theorem or SOHCAHTOA. Either you got Pythagorean theorem or those are your only choices. Okay, Pythagorean theorem or SOHCAHTOA. Now we're not talking about angles here. So we'll save SOHCAHTOA for another one where we would talk about angles. Since we're not talking about angles, we're going to talk about Pythagorean theorem. So what's the geometry here? Okay, x squared, which is the hypotenuse, would be equal to s squared plus p squared. All of these things are moving. Side S is moving because the suspect is moving. Side P is moving because the policeman is moving. And the x distance between them is moving as those two pieces move. Everything is related to each other. So now we're ready to put this actually in motion, and we're ready to take the derivative of all of these things. So what's the derivative of x squared?
2x dx dt.
Okay, 2x dx dt. And the dx dt is measuring how much the x side is expanding or changing. And then on my s squared, I have 2s ds dt. And ds dt we expect to be a positive number because ds dt is the speed or the changing of the suspect's position. And then we have 2p dp dt, which is the changing of the policeman's position. So we did our geometry first, now we did our calculus, and now we're ready to drop in some of our values. So where do we put the 80? The 80 is for P? No. Okay, the 80 is a miles per hour. So it's not a P, it's a dp dt. Okay, it is a rate because it has the 8 miles per hour in it. And he's going 80, but we expected it to be a negative number. And so we can't just put in 80. We have to put in negative 80. That's because his side is shrinking. Okay, his side, the policeman's side, is getting smaller. What do I do with the 20? Okay, that's the distance between them, and it's increasing, so it stays positive, and that will go in for 20. And I have 2x. And then what I'm left with are all the other variables, so I've used up everything I have. And so how fast is the suspect going? Well, now we want to manipulate these things, move the variables around to get ds dt alone. So I've got 40x equals 2s times ds dt minus 160p. And so you should be able to quickly move the 160p to the other side. You should be able to divide and get ds dt by itself. So s dt is going to end up with a numerator that has what in it? 40x plus 160p, and then a denominator of 2s. And that can be reduced because everything has a factor of 2. So it could be 20x plus 80p over s. And the units on this, the numerator has to have a unit. Okay, and this is the suspect we're talking about. So what would the suspect's units be? Also miles per hour. And it turns out to be positive. And we expected it to be positive because the suspect is gaining and going off in that direction. Okay, any questions on that one?
Why did they expect the police? Oh, because that distance is shrinking.
Right. Maybe it would have been better if I'd drawn it upside down. If I had drawn it like this, sometimes that helps. And say the policeman is going that way. People are like, oh, because the arrow is pointing down, then, but it doesn't have to do with the arrow. It has to do with what the side is doing. His side is shrinking. Okay, his side is shrinking. Okay. All right, so as soon as we specify a particular moment in time, all motion stops, and it's like we freeze frame. Okay, so when you see words like at the moment of, that means you're stopping all time at that moment, or when the value is, you just stop. But you really want to make sure that you do that last, okay? That's going to mess up all your math if you plug in time too soon. Plug in time at the end. Okay. My friends just went out to New Mexico to see one of the hot air balloon shows. That's on my bucket list someday. I want to get out there and see that, but let's talk about that. An observer is watching a hot air balloon rise. So here's my hot air balloon. Okay, and then I've got a person over here watching this happen. And this is going to form another right triangle for us. Okay? Don't put numbers in too soon. I'll call this X for the person. I notice that they're talking about the angle for the balloon, so it means I'm going to need to draw a line here and put an angle in. So I have a theta, and I have H for the height of the balloon. No numbers, okay? No numbers. Again, we have a right triangle, so my geometry is actually trigonometry here. So I've got some trig going on. All right, so last time we did the right triangle of Pythagoras. What's our right triangle going on here? Okay, tangent. All right, so tangent of theta is what over what?
H over X.
H over X. Okay, this is the trig. Get that done first. No numbers. Okay, now we're going to put the balloon in motion by taking the derivative. Okay, we got to reach way back. What's the derivative of tangent? Secant squared. And then what do we do with the parentheses?
Keep it.
Keep it. Then what do we do after that?
Take the derivative.
Because theta is a variable. It's not like pi. It is a variable. So what's the derivative of that? D theta dt. Okay, then we have on the other side, what rule are we going to need? Quotient rule. And we start with x, low, and then multiply by dh dt minus h times dx dt all over x squared. Okay, all the dt things means something is moving. So what does d theta dt mean? The angle is moving. Can you imagine your neck going like this? Okay, your angle is moving. All right, what does dh dt stand for? The balloon. The balloon is moving. Okay, and what does dx dt stand for? The person is the...
Or the balloon is moving.
Okay, that's dh dt. The balloon is moving. Oh, yeah, we're not doing any wind here. We're going straight up. That would be a whole nother variable. We'd have to have a W in here, so we're not going to do that quite yet. All right, but what about the person?
The person's not moving.
Person's not moving.
X doesn't change.
The person is standing still. So what can I do with that? 0. And that's going to clean that out for me. Now I can plug in the other values. What do I do with the 200 meters? That goes in for X. That's the distance. Okay, so now I'm going back to plug in X to be 200. So that'll give me 200 times dH dt over 200 squared, which I can reduce. On the other side, okay, what do I do with the 10 degrees per minute? Okay, degrees, what is that measuring? A theta, and the minute is measuring a time, and so we put that in for d theta dt, that's 10. Okay. At the moment the balloon is 1,000, where do I put the 1,000? Ooh. I put it on the picture.
No, not yet.
Okay? There's no H in my problem. Okay? So why would they have given me the H of 1,000?
Because that's the instantaneous.
I don't need to, so that I can figure out what secant theta is. What do I need for secant? It's 1 over cosine. What do I need for cosine? I need adjacent, which is 200, and I need hypotenuse, which I'm going to need to quickly figure out because I don't have hypotenuse, but that's why they gave you the 1,000, so you can figure out what the hypotenuse is, all right? Nick's got his calculator out. You got it for us? No, he doesn't. Okay, can somebody figure out the hypotenuse for us quickly in a minute? It's not hard. How do you do it?
I'm still trying to figure out what I'm doing. Where this 1,000 is being dropped.
Okay, right here. The 1,000 got dropped right here. The balloon is 1,000 high. No, give me an exact number. Give me the square root of. Don't give me no decimal. That's terrible. Give me.
So are we saying the cosine of 10?
We don't know what the cosine is yet. We've got to figure it out. Got it for me? It's got to be, okay, I can do this faster in my head. 1,000 squared, that's 1,000,000, and then plus 200 squared, that's 40,000. So 1,040,000. Okay, so what is the secant? What's the cosine? Come on, what's the cosine? You can do this. I know you can do this. I believe in you. Cosine, adjacent over hypotenuse. So what's the cosine? 200 over that Ucky square root. What is the secant? The square root over 200. So the secant is the square root of 1,040,000 over 200. And what do I do with that? I square it. At that point, you can use your calculator to help you figure out what dH dt is going to be, which is going to be the speed of the balloon, because I used h to stand for my balloon's height. So what would you do first, maybe?
Solve for the left.
Yeah, I let my calculator do all the left side. I mean, I would just type all that into my calculator. But
And then multiply.
I would, yeah, I mean, I would, if you square it, you're going to get 104000 over 200 squared. Yeah, multiply both sides by 200 squared, for sure. For sure. So this is times 10, and then on the other side, you've got 200 dH dt over 200 squared. They're both over 200 squared. So if they're both over 200 squared, those reduce each other out. So that's what you've got left. Divide by 200 and you'll have the answer. I'll let you do the calculator part. Okay, last one. Okay, a cone. This cone is 20 centimeters deep. It has a radius of 5, which means it has a diameter of what? 10. Very good. Okay, it's being filled with ice cream at a rate of 3 cubic centimeters per second. And the fact that we're seeing cubic centimeters clues us into what geometry going on here. Okay, so pay attention to words. Cubic centimeter means we'll be dealing with volume, okay? So I got to keep that in mind. I'm dealing with volume. How fast, so there's the calculus question, is the depth of the cone changing when the ice cream gets to 12 centimeters deep? All right, so this is a massive cone. 20 centimeters, 5 centimeters. This is huge, okay? The difference between this one and the water problem, well, first of all, the water problem was leaking, so the water was going down. This one is going up. But the biggest key difference is that unlike the water problem, what else is changing in this problem? The radius, okay? So that is key because before we did have, we had 3 variables. We had volume, radius, and height. But in the context of the cylinder problem, the radius never changed. So it was a non-factor because it had a value of 0 when we took the derivative. In this case, the radius is changing as well as the height. So we've got an additional variable we need to worry about. However, it is changing proportionally. The thing about cones is that once you know the ratio of the cone in terms of its dimensions, those ratios will be preserved no matter what. So in other words, if this is 20 to 5 right now, I would say, well, what if it was only at 10? What would the radius be? 2.5, okay? Because if you cut the height in half, you have to cut the radius in half. And if you cut that in half again, so if you go down to a height of 5, what would the radius be? Half of that, 1.25. That is a key geometric concept that you have to pull out of the depths of your memory to remember, okay, I'm going to use that. And this is how we're going to use that. We just use good old-fashioned cross multiplication proportions. All right, we use the fact that the proportion of radius to height starts out at a value of 5 to 20. That's the proportions that we're given. So using cross multiplication, 20r will always be equal to 5h. And you could simplify that. How could you simplify that?
Divide by 5.
Okay, divide by 5. So that would tell you that 4r equals 1h. That is going to be helpful to you, knowing that that geometric, and that only works in cones. Okay. All right, so let's do our geometry first. Our geometry is the equation for the volume of a cone. Anybody know what that is?
1/3 r squared times that.
Okay, do you know what the volume of a cylinder is? We did that one before. Pi r squared h. If it's a cone with a pointy tip, you cut it in thirds. Okay, same thing is true for a pyramid. Okay, gonna cut it in thirds because it has a pointy tip. All right, so we've got 1/3 pi r squared. However, we also know the algebra from here. So we can replace one of the variables like we did before when we were doing our box problems. Okay, what variable would you like to replace?
H.
Okay. Now, read the problem a little bit more carefully. Okay, what's the question asking you? The question is asking you how fast is the what changing? How fast is the depth of the cone? Which means you want to keep h in the problem. So you don't want to get rid of h, you'd like to keep h. Which means we need to get rid of what other variable?
The R.
The r. So how would you get rid of the r?
Multiply everything by 4.
Divide by
Well, okay, look back at the yellow circle. If 4r is equal to 1h, what's an equivalent statement on that?
1/4 each.
Okay, r, 1r is equal to 1/4 of h. That's what you want. That's the algebra. So this is a combination of geometry and algebra. Again, it's always the geometry and the algebra. That's the hardest part. It's never the calculus part. It's always the geometry and the algebra. So let's replace the r with 1/4 of h squared instead of r squared. Then we can clean this up. So what will the numerator ultimately be? Pi h cubed And what will the denominator ultimately have in it? 48, or we can write that as, so you can write it as 48, or you can write it as 1/48 out front. So 1/48 pi h cubed. If you do the hard work of that at the beginning, it makes your calculus very, very easy. Okay, this is all the geometry and the algebra. Now we're ready to bring calculus into action. So we will take the derivative. So dv dt, that's the rate of the volume of the ice cream being added into this cone. And then how do I take a derivative on the other side, knowing I have a 1/48, which is a constant, a pi is a constant?
Take the 5 and 1/48 out.
Okay, take the 1, and what do we do with the 3?
We multiply it in the front.
Okay, so we're going to pull the 3 to the front. So that'll be 3 in front of 1/48 in pi. And then what happens to the h? H squared. And what else happens? dH dt. And now our calculus is done. And now we can start dropping the values in. Okay, so we've used the 20. We've used the 5. That was when the cone was empty. When the cone was empty, we had a depth of 20 and a radius of 5. The cone is now being filled. And so I need to put in the 3 cubic centimeters per second. Where will that go? Okay, that's the dv dt. Is it positive or negative?
Positive because it's filling.
Because it's filling up. Okay, and the other side I have 3 and 1/48. That reduces to 1/16 pi. And what am I putting in for h? 12 squared, and then I have dH dt, and then it's just a matter of getting that all nicely by itself so that I can solve. So I'm going to multiply both sides by 16. That'll give me 48 equals 144 pi dH dt, so I can get dH dt alone. So dH dt would be a numerator of 48, a denominator of 144 pi. And those do have a number in common. What number do they have in common? 24. Very good. They do have 12. They do have 4, but I think 24 is the highest. Okay.
Keep reducing.
Just keep reducing and keep reducing and keep reducing. So if you reduced by 12, you'd have 4/12. If you reduce that, not only do they only have 24, they have 48 in common. 48 goes into both of them. Okay. So 1/3 pi. And then what's the numerator? What are the units? What would the numerator, if it's dH over dt, h is centimeters and time is seconds.